Hi. Hi, students. Welcome to Introduction to AI and the Law. Today, I've brought in an expert to talk with you about an overview of artificial intelligence and machine learning. And so I'm going to introduce my friend, Dr. Benjamin Chung.
Hi, so my name is Ben Chong. I work in Nokia, and today I'll be giving an overview of AI and ML. Just a little bit about myself. I work on Open Network Automated Platform, ONAP, and 5G wireless systems, zero test management, orchestration, and modeling architectures. I work in OREN standards and what they call Working Group 5 or 6, which is the 5G cloudification, O2 orchestration, and Working Group 1 architecture, network slicing, and 5G wireless standards development. So my organization is part of what's called S&T, Strategy and Technology, which is Bell Labs is also part of that organization. I've been in the wireless industry for 27 years, working on 2G TDMA and 3G UMTS and 4G LTE and now 5G, and starting to work on 6G. I worked at Lucent Technologies, Lucent, and now Nokia. They've been transitioned from one company to another. I've been in software development, system engineering, and architecture. I was a developer at General Electric Medical Systems, working on ultrasound and MRI machines. I have a number of patents. I have my master's in electrical engineering from Purdue, a PhD in operations research from Walden. My hobbies, I like traveling. I've been to 31 countries around the world and 6 continents. Photography, I'm trilingual. I've written 6 books, the latest of which are the Periodic Table of Ideas and the 4 Elements of Thinking. I've published 15 games, and I was a former World HeroClix champion, and I'm an amateur magician. Okay, so I'm going to go over the big ideas in AI and ML, give you some of the key concepts and a high-level overview. And then we'll break off and talk about machine learning in a little bit more detail, some of the key ideas and big methods there. And I'll give you a little bit about the history, the past, present, and what I think is a little bit of the future of the AI history and milestones. And then we'll talk about some AI/ML applications and how it's used and what are some practical applications and some of the AI/ML players. So before we talk about artificial intelligence, maybe we take a step back and think about what is intelligence in general. So, and there's many ways to view and think about intelligence, but here's some ways to think about it, right? So it's the ability to learn, to obtain and process new information, the ability to reason, to manipulate information, to be able to comprehend and understand information, to grasp truths and determine the validity of manipulated information, to be able to see connections and linkages and relationships, to divine how validated data intersects with other data, to consider meanings, to apply truths to situations, and separate fact from belief, determining if data is supported by probable sources that can be demonstrated to be consistently valid. So I think as we move into an era where you'll hear a lot more of AI in the news and robotics and so forth, these sorts of questions will constantly come up as what separates machine intelligence from human intelligence, and is there a separation? And that opens the door for a lot of questions and a lot of gray areas. So there's 4 kind of big, let's say, concepts that I'd like you to walk away with from this talk. And the first is artificial intelligence, so that are programs and machines that learn, reason, and make intelligent decisions. The second is machine learning, so machines that learn through experience without explicit programming. Third is neural networks, which are connected elements that process data, adapt, and learn from past patterns. And then deep learning, which are artificial neural networks that can adapt, learn, and make intelligent decisions. Now, to be clear, machine learning is a part of artificial intelligence. Neural networks is a part of machine learning, and deep learning uses neural networks. So they're related concepts, but these are, I think, some of the biggest ideas in this overview that I'd like you to walk away with. So let's talk about the first one, artificial intelligence. And there's sort of 3 pillars or 3 categories of artificial intelligence that characterize it. So the first is artificial narrow intelligence. It's also called weak AI. And basically, it's kind of like it sounds. It's a very narrow form. It can do just a narrow set of activities. You might have heard of in the 1980s expert systems. It takes an algorithmic approach to solving problems. It utilizes data mining and pattern recognition, and it's very good for human-computer partnerships and navigation systems. It performs a narrow set of activities, basically. So we're basically in this era now of really productive artificial narrow intelligence. While that sounds kind of like weak AI, it sounds, it doesn't sound very useful or very adaptive or very powerful. It actually, just the things that we've been able to do with artificial narrow intelligence, which we'll talk about throughout this overview, is really amazing and growing by the day. Artificial general intelligence, or strong AI, is the ability to recognize, learn, be able to see and interact with its environment and process language. So you see some of the things that we're doing now really border on strong AI. So facial recognition and picture recognition, be able to a machine to learn, to be able to process vision and process language, NLP, natural language processing, and NLU, natural language understanding, and NLG, natural language generation. We're kind of bordering on a lot of these things, at least sort of separately, right? So, and then artificial superintelligence is sort of a transcendent AI that's able to innovate. It's creative. Maybe it's self-aware. It's able to decide. It's able to plan. Maybe it is able to forecast what it wants to do, and really is advanced robotics and communications embodies this artificial superintelligence. So, and there won't be. I think it's important to emphasize there won't be, uh, um, there won't be huge discontinuous steps in these. There'll probably be more gradual transitions from one thing to another. So. An example of artificial narrow intelligence is things like Bard, ChatGPT, Echo, and Alexa that have kind of a narrow function. Bard is a chat bot, something that can understand your language and respond. Or Echo, who can set your house lights to 50%. Artificial general intelligence is something like maybe you see in the movies like Wall-E or C-3PO, something that can learn, talk, and engage its environment dynamically. And then an example of maybe artificial superintelligence is something like Megan from the movie Megan, or Data from Star Trek, or AI from the movie AI. Something that's maybe self-aware, that's creative, that can contemplate, and is may possibly conscious. Okay, so next let's dive into machine learning. So I'll talk about some of the big ideas in machine learning, and really there's four major categories or four major types of machine learning. One is unsupervised learning. The second is supervised learning, semi-supervised learning, and reinforcement learning. So in unsupervised learning, the machine is finding hidden patterns and data groupings by itself. It's data driven, it's identifying clusters of things. So you can sort of think of a machine kind of playing with Legos, and it builds something or finds something on its own without any kind of supervision at all. In supervised learning, there's some labeled data sets which help train it. It's task driven and it can predict values. It's looking for some kind of target. So you train it to a specific thing that it's trying to learn against. So you can think of an archer shooting at a bullseye. There's a specific point on that center of that bullseye, or just the bullseye itself, that it's the target itself, the concentric rings that you're trying to hit an arrow on. So it's you're telling it this is a particular thing that it can compare against.
One of my favorite examples of that is Getty Images. One
Oh
reason
yeah,
that all of the image places want to train on Getty Images is they have just super detailed metadata or labeling on their pictures, which makes it easier to train the AI to recognize those things.
absolutely. Yeah, that's a good example. So for semi-supervised learning, I think a good model or to think a mental model to think about that. It's a model of mixed label and unlabeled data, categories, suggestions, and examples. But a good model to think about that is like a teacher in a classroom. So the teacher describes certain information. It describes certain sort of learning targets, and it describes it helps it supervises to some degree. But then after that, you take an exam, and then in that exam, it's sort of unsupervised. You're trying to figure out problems. You're trying to solve something, and maybe there's a right answer, but maybe there's not. But you're kind of, it's half supervised and half unsupervised. In reinforcement learning, you have some input data and there's a correct output data, and it can learn from its mistakes. And these are really powerful algorithms that have been used to do very specific things like, play Go or play chess, or play a video game. But those things use reinforcement learning. So we'll talk about each of these different areas. In unsupervised learning, it's clustering unlabeled data sets. It can use dimensionality reduction. Supervised learning classifies data. It uses regression. We'll talk about that. So semi and supervised learning it uses label and unlabeled data, categories and examples. And reinforcement learning can make real-time decisions. It can acquire skills and learn tasks. So again, at a high level, we can think of supervised learning as in this cartoon as, you're showing it a picture of what are apples, and you're trying to have this thing train on images of our apples, but you tell it, this is what an apple, these things that it's classifying into apples, that you're guiding it to say this is what the thing I'm looking for. In unsupervised learning, the machine is finding patterns on its own, but there's nothing telling it that it's the right thing or not. It's just finding these patterns on its own, which can itself be, very powerful. We'll see different examples of these coming up. So I'm going to talk about some algorithms, some of the bigger ideas in each of these four categories. But just to note, this is just an overview. So every one of these areas has many, many, many algorithms and decades of work behind it. I'm only just scratching the surface, and in each of these, I will talk about each of these, and I'll try to. There are some equations. I'll try to explain it in as sort of commonsensical terms as best I can here. So for unsupervised learning, I'll be talking about a priori association, k-means clustering, artificial neural networks. For supervised learning, I'll be talking about linear regression, support vector machines, decision tree classification. Semi-supervised learning, generative adversarial networks, or otherwise known as GANs. And then self-trained naive Bayes classifiers for in semi-supervised learning. And then in reinforcement learning, we'll be talking about model-based estimation and Q-learning. Now, there are many, many algorithms that I'm not going to be talking about, but these are kind of the biggest ones, I feel. So these are, when you start learning about these in any particular area, I think these are some of the big hitters. These are some of the biggest ideas in each of these areas. So in unsupervised learning and a priori association, it's much easier, I think, to learn this concept through an example. So but some of the key ideas, though, the three big sort of key ideas here is a support, confidence, and lift. So let's take a look at a video recommendation system. So think of like a movie system like, I don't know, like Vudu or Movies Anywhere, or Netflix, where I'm trying to design a system where I want to recommend a movie to somebody. So I know they've seen some movie, and do we think they'll like another movie? So in this case, given that somebody has seen Wall-E, do we think that they'll like Marjorie Prime, right? Those are two movies that I really like. I picked two AI movies on purpose. So the blue faces are at the blue faces plus the green faces are people that have seen both Wall-E and Marjorie Prime. The green faces are the ones that have only seen Marjorie Prime, and the yellow faces are represent everybody else, right? So, and I put a sort of smiley face there because it's the assumption that if you've seen the movie, you liked it, right? So the total number of elements in those equations are the total number of users of the system. So suppose in Movies Anywhere has a total of 100 users. Okay, so again, I'm greatly simplifying a lot of things in order to try to explain this. So the support is basically it's the number of elements that have seen Marjorie Prime over the total number of users. So let's say that's 10%. The confidence is that will recommend Marjorie Prime to the people that have seen Wally. So that's the number of elements with both X and Y is 9 over 40, the total number of people who've seen Wally, and that's 22.5%. The lift then is the sort of calculation of a confidence of how good we think that recommendation will be. Now, this is again a very simplistic. This is the most the algorithms that are actually used by Voodoo and Movies Anywhere and Netflix are much more sophisticated than this, but it illustrates one powerful idea in machine learning, and this is sort of this unsupervised learning where you can find associations between data and relationships. So in its most simplest form and its essence of the idea is that you're calculating support and confidence levels. You're looking at subsets of items in order to try to improve the lift. Okay, the next idea we'll look at in unsupervised machine learning is called k-means clustering, and that's a mouthful, but basically, you take a bunch of data, and here we're in the leftmost point number 1. You're randomly selecting clusters. So you have a red cluster, a green cluster, and a blue cluster. Now those are kind of randomized, so you can kind of pick any data points you want. And in this case, the northernmost point there is the red cluster, and the kind of south of that is the green cluster, and to the right of that is the blue cluster. And what you're doing is you're going to take all your other data points and calculate like a Euclidean distance to them. And I drew a little diagram there showing that. I should probably turn my pointer on here. So I drew this little Euclidean distance thing. You can calculate from the data point to the means here. So we have three means, 3 cluster centers. And you're trying to calculate the distance from each of these data points to this particular mean that you've chosen. So in this case, we have a data point. We see where the data point is, and then we'll find the centroid of that, what is called a Voronoi area. But essentially, this is just fancy words for saying, once we find the means to this, we'll try to find the sort of central point that's the center balance of all those data points that we found to be closest. So this red data point is closest to this red center, and all these data points are closest to this green center. All these data points are closest to this blue center. And again, it's just through this simple Euclidean distance, at least in 2 dimensions. You might be working at higher dimensions or lower dimensions. So
It
once you
seems like, go ahead, sorry.
Yeah, so once you find that centroid, then you repeat. So you repeat this process, and they'll converge. So you notice that the red thing has grown because we found as the centroid moves here, this data point is actually quite close or closer. It becomes closer to the red centroid than it was to the green one, and so that data point sort of migrates to this red center, and it keeps. If you look at, say, like videos, you can look for videos online. You'll see it's kind of interesting. You'll see how the animations of the centroids moving and it's sort of converging on solutions are kind of interesting. So, yeah, do you have a question? Yeah.
I was gonna say, can you give an example of how this might be used? It feels like maybe polling data might be an example.
Yeah, so actually, for all of these, I'll give examples to later on. So I have a whole slide on how each one of these is used typically.
Okay.
So for every one of these, I have some examples, but it can be used just to answer the question directly now. It can be used for any kind of like data that has 3 sort of answers, like polling data, that's sort of a classification data. It can anything that kind of falls into those sort of category type things. And again, this is unsupervised, so the idea is we have a bunch of pictures of fruit, and we're trying to, we've represented a vector representation of fruitiness, and maybe there's, here's an apple and here's a banana type fruit and an orange type fruit. It just doesn't know anything about what those fruits are, but it just classifies them. Well, I think these pictures are all pictures of bananas, and these pictures are all pictures of apples, and these pictures are all pictures of oranges. So you can use it for a whole bunch of things, but like, image classification, any kind of classification is a use of k-means clustering. It
Great.
was it was developed by Stuart Lloyd of Bell Labs in 1957, used for pulse code modulation. Ed Forgy in 1965 also introduced a similar concept, and it's also sometimes known as the Lloyd-Forgy algorithm. So you might hear that as well. Oh yeah, you're about to say something.
No, I was just say that all makes sense. Thank you.
Yeah. Okay, you're welcome. Okay, so the next is this is kind of a bigger topic. Like some of the other ideas we'll talk about are kind of more self-contained topics. Artificial neural networks is a big topic, and that hence it's one of the sort of big pillar ideas in this overview. And there's lots of different kinds of artificial neural networks. So we'll talk about 4 of them here. Each one of these could be a whole hour-long lecture by itself. And again, I'm just touching the surface of the topic. So autoencoders learn to code unlabeled data and copies its input to output. It encodes that data to transforming that input data. There's some sort of decoding function that then recreates the input data from the encoding representation. And usually during the encoding, there's some savings or compression that can happen. So I have it encodes it to a lower dimension representation. So an example, I think a good example of this is like image analysis for handwritten data. If it's trying to OCR, optical character recognition for letters or numbers, it can basically it takes on inputs and then compresses that, encodes it, and then it can decode it back into an image. And in the ASCII representation, it can represent a handwritten digit, which can take lots and lots and lots of bits to represent somebody writing 4. If that were a photograph of a 4, and if it could encode it into just 0100, it uses a few bits, right? So it can be very efficient depending on what you're trying to encode and decode here. Recurrent neural networks are characterized by the direction of flow of information between its layers. It's a sort of it uses a feedback loop. It's a bidirectional artificial neural network. It allows the input from some nodes to affect subsequent nodes in the same node. So there's some inputs, it does some processing, and that processing that it does can feed back into itself, into the output. So we see here in the little diagram, we have green as the input, the H is the state or processing, and that feeds backwards into the system into an output. And that same thing, if you kind of unfold it, it has different states that it goes to, and it takes those inputs and it's feeding it into the next states. In a feed-forward neural network, it's characterized just by the direction of flow between its layers, so the data moves in only one direction from an input layer to hidden layers to an output layer in a feed-forward neural network. So it's taking information in, ingesting it, and it goes through some intermediate process layers to output layers. Convolutional neural networks are a special form of neural network that is really optimized for processing images. So its main purpose is to handle images. So it learns feature engineering, meaning like edges, and if you're trying to identify like a cat, like those are its ears, or this sort of edge is the edge of, here's the edge of the outline of the border of the cat. And convolutional networks are really specialized to process images. It looks at vanishing gradients, exploding gradients. It's seen during backpropagation. Which is, again, that sort of feedback type. Actually, backpropagation is the feedback along a vector, and you can calculate the amount of data along that. Think of like an X-ray, like that passes through an image, and you can calculate a weight along that X-ray. So it has multiple layers as well that are each sort of tailored to help process that image. There's a long, rich, and deep history of neural networks, and going back to linear regression, and but one of the big steps, I think, and we'll talk more about the history of this, but the Warren McCulloch and Walter Pitts neural networks in 1943 is probably one of the more major milestones. Okay, and I left off on purpose GANs here, so we'll talk about those later, but that's also a form of neural network as well. Linear regression is supervised learning. So here we're looking for a particular target. We have a bunch of incoming data, training data set. There's this algorithm that is looking at the incoming data, and it's looking at a particular kind of output against a linear combination of dependent input variables. So basically, if we're trying to determine if something is a vehicle or a car, let's say an automobile, for a sedan, like a four-wheeled vehicle, we may be looking at the height, weight, and dimensions. For example, we might characterize something like mobility, how fast this thing we think is going, and so those are examples of dependent variables. And then the those input variables, and this sort of output variable is a dependent variable is a comment of these independent input variables. So that the dependent output variable might be, carness, right? So we have some number to represent how car-like this thing is. So we calculate this output dependent variable from a combination of linear input variables. And again, this is a supervised learning. So we have a particular target we're aiming towards, and the linear regression best fits the data points as best we can, finding the what's called a regression line to fit to fit the data as best we can to something that we're trying to determine. Support vector machines, again, is another kind of supervised learning. Here I'm showing an example of you're trying to figure out, is this image a picture of a cat or a dog? And you'll somehow classify features of this thing. So, how many legs does it have? How furry is it? What are its ears like? You find some ways to characterize features of this thing. And in that feature space, you'll map those things into a feature space, and so you'll have data points that these red points are things that have sort of cat-like qualities, and these things are things these data feature points have more kind of dog-like qualities. So maybe the sounds it makes is more barky-like, and the sounds it makes here are more meowy-like, right? So there's some ways you've classified your data according to some sort of features, and and you'll notice that's somewhat vague. So how you define the problem is very important, and how you classify features is very important, and that's going to determine how well your algorithm works. But what you do is basically you find what are called support vectors. So you're going to find a dividing line, essentially. So that's the fancy term they use is a hyperplane. So basically, if you look at the blue line here, this divides the class 2 features against the class 1 features, and that's just a fancy word to say, this is a line that I draw that best divides these two bunches of data. Now, the data that sits along the other ends of this dividing line are called support vectors, and that's hence why it's called the support vector machine. So in this example up here, you can see maybe a little clearer. There's a dividing line between these two sets of data points, and these yellow lines these yellow dots are the lines that are closest to this dividing line, and these dark blue dots or data points are the ones that are closest to the the dividing line. And what the algorithm is really trying to do is you're trying to maximize the margin around the separating hyperplane. So these dotted lines, the sort of margin between the solid blue line and this dotted line, what you're trying to do is find a line that maximizes the separation between these two data points. So that's pretty commonsensical, right? So basically you want to find a dividing line such that there's the maximum amount of gap between these two groups of data points. Um, and what's interesting is this algorithm is not new. It's been around since 1964 from Vladimir Vapnik and Alexei Chernovnikis. So the concept of this algorithm has been around for quite a while, but it's used in machine learning today because computers are really great at crunching information. And also, it's also important, and I'll talk a little bit during the history, that computing powers has also increased dramatically through Moore's law over many decades into the 1950s, and that's greatly facilitated the use of these algorithms that have been around for a long time, but we're able to use them in a very powerful fashion today. Okay, another example of supervised learning is called decision tree classification. And a simple way of thinking about this is kind of like the 20 questions game. So you have I have the little cartoon machine learning robot here, and it's trying to see, hey, I see a picture of something, and what is that thing, and it can ask and classify some really basic questions. These are called branches. So is it alive? Yes or no. Another branch might be, does it fly? Yes or no. And is it able to carry a number of people? Yes or no. And so through a bunch of these questions, it kind of can make a decision. It goes down to a leaf of the tree, and it determines that this thing is an automobile, right? So from the roots and nodes, it performs some classification. It goes from observations in the branches to conclusions about the items of the leaves. It uses statistics. It's used in statistics, data mining, and machine learning. And classification tree models are classification tree models targets discrete sets of data. So this is particularly good when you have a finite set of things that you want to classify, like perhaps there are different kinds of, I don't know, passengers in an airline. Like, these particular passengers have, certain security concerns or have certain dietary needs or whatever. And does it fit into this kind of, is it a special traveler and so forth? So, okay. The next is called generative adversarial networks. It was developed by Ian Goodfellow in 2014. And the basic idea is that it's a good way to think about this is it's two artificial intelligent networks, neural networks, facing off against each other. So they're two neural networks that are pitted against each other, kind of in a zero-sum game. So the network's trained by evaluating inputs in an unsupervised manner. It's characterized by, you have in this example here, we see there are actual photographs that it's trying that you're going to feed into this one algorithm to try to determine whether this is a dog or cat, let's say. And you have another neural network that's trying to fool it, right? So it's adversarially creating artificial computer generated faces that look very much like dogs. And this discriminator neural network is trying to determine if this dog face is fake or real. So this is a really, really simple example of again, generative adversarial network but the basic idea is that you have one or more neural networks sort of pitted against each other in order to make them better. So the generator becomes better, and it eventually becomes better at trying to fool the discriminator, and hence the discriminator becomes better at discerning what's real and what's not. Okay. In the area of semi-supervised learning, we'll talk about self-trained, naive Bayes classifiers, and that's really a mouthful. And this is really, when you start studying this, you'll always find things about the Bayes theorem. So that's a really simple or a very fundamental mathematical equation, right? Given that, what's the chance I'd observe H, given that I've already observed X? That's the probability of X happening, given that I've already observed H times the probability of H times divided by the probability of X. So that isn't very so easy to picture of what that means, right? So I think this is best. The easiest way to learn this, I think, is again through an example, and this is also one possible or maybe sort of common use of this kind of algorithm, right? So I'm trying to differentiate normal emails against spam emails. So it's a classification type procedure and application. And suppose the probability that a normal email is 2/3 or 66%. And here I'm just showing you, suppose your entire sum body of all the emails you've ever gotten your whole life is 9 emails, right? And 6 of those we know are normal emails, and 3 of the emails you've gotten are spam emails, right? So we have a really rough estimate of, well, about 2/3 of the emails you get are normal emails, and about 1/3 of the emails you get are spam. Now, what you do is you're going to look at all of the emails, all your whole body of data points, and you're going to classify them into words. So how often does the word dear or love or discuss or lunch occur in normal emails? Well, those words occur kind of more often than the word $1,000,000 in bank, which happens to occur a lot more often in spam emails, right? So give me $1,000,000 and deposit it in my bank. And each of these little squares I drew just represents, this is how many times it occurred. So if we look against all of our normal emails, the word dear occurred 11 times. And if you count all these little blue boxes, there's 31 little blue boxes. So let's say all of the emails, for these words, occurred a total of 31 instances, and 11 of those instances were the word dear. So the first thing you want to do is create a histogram of all the words from normal messages. You want to calculate the word probability. So given that it's a normal message, again, here we're hinting at the Bayes theorem here. We're looking at the probability of the word dear, given that it's a normal message, right? So, and the chance that I use the word dear in a normal message is 11/31. And you can calculate that probability for all these other things as well. Now suppose we want to look at two words occurring together, $1,000,000, right? So the chance that the word million and dollars occurs together in a normal email is 2/3, the chance that it's a normal email in general, times 1/31. So it's, the word million and dollars don't occur very often in a normal email. So those are each 1/31, and you end up with just a 0.06%. However, if we look at a spam email, we'll see that the word million occurs quite a number of times, and dollars even more. And again, we can calculate their probabilities, the chance that in general are that it's a likelihood that it's a spam email, given multiplied by the probability that we use the word million, which is 4/21. If you count, there's 4 of these red boxes divided by 21 total red boxes, multiplied by dollars, given that that should be a S there, given that it's a spam email. And the method is naive. We say it's naive because it doesn't considering the order of the words. So in this case, this algorithm doesn't differentiate between dollars and $1,000,000. So we in our heads, associate, well, you would deposit $1,000,000 in a bank, right? But for it's naive because it doesn't care about the ordering. This math just simply, it's like drawing say colored beads out of a bag, right? So it doesn't care about the ordering. It's just how often does these words occur. So it's a self-training method that trains on data by probability statistics, the Bayes theorem, to classify data sets to be analyzed, and it's semi-supervised because it trains on some known sample data. So, and of course, actual email filtering algorithms are much more sophisticated than this, but this gives you the basic idea of what a self-trained naive Bayes classifier is. Okay, next let's move on to reinforcement. The two reinforcement key reinforcement algorithms. One is called model-based value estimation, and the other is called Q-learning. So, and Q-learning we'll talk about on the next slide. So, for model-based value estimation, we can't get away from this equation because it's so crucial to the idea. So this is called Bellman's equation, and it's full of stuff, but hopefully after I explain it a little bit, you'll get it. So in any particular kind of thing, so think of, well, let's take the example of a computer car racing game. So there's you're trying to control one of these little digital cars. So that's the agent. And that digital car is racing along a track. That's called the environment. So you have some kind of something doing something in some kind of environment. That's pretty simple, right? So you have this little car, or you have this little Mario Brother thing, or you have a chessboard. You have some kind of thing that's in some kind of environment. Okay, very simply. And that agent can observe its environment. So it sees that it's about to go along a track, it's going on a straightaway, going along an S-curve bend. It's observing its environment to some degree. And it's able to take some kind of action in that environment. So perhaps it can make a turn, it can accelerate, it can decelerate, it can go on a straightaway. So it's able to take some kind of set amount of actions in that particular state. At time t, it's able to take some kind of action, and in the next tick of time, maybe a second later or whatever, it takes a different action. Okay, and it arrives at some particular state that you characterize. So you're going to characterize the state of, say, a chessboard, or a state of the state of game. The yellow car's here, the blue car's here, the red car's there, in a particular state of the system. And you're going to get some kind of reward from taking some kind of action given a particular state in the environment. And that reward is, in this case, how good am I ahead of the cars, or what's my measure of being on the track? So as in the physics of this, I try to take this turn, this sharp sort of U-turn, maybe the speed or acceleration or gas that I apply to this digital car is one of the actions, or one of the things I can do. And how sort of well did I take that curve? Am I still on the track? Is a measure of the reward. And through that, I can create a policy, and you'll see that in the literature as pi. So I'll have some kind of policy given a state and given an action. I'm gonna create some kind of rule, basically. So given some state and given some action, like I'm coming against this curve, I want to slow down a little bit, or I'm on a straightaway, I can speed up a lot. I have some sort of rule of what I want to do given a particular environment and state. And that's the basic, if you got that, that's the basic idea of model-based value estimation. Bellman's equation, the key idea in Bellman's equation, there's a lot of symbols here, but the key idea is that basically I don't have to understand the entire universe of the system. I don't have to understand all the possible states, and like all the possible chessboard patterns is a bazillion, right? All I really need to understand is, given a particular reward at a particular time, I can if I can calculate the total amount of rewards, the value of this is the value of the quality of the state of all the future states, then I can basically just look at the current state and make a decision. And I know that's kind of a mouthful, but here's a kind of simple way to think about this. So if we look at a chessboard, I can kind of look at a chessboard, and I can make a decision based on the current state of the chessboard. And what I can do is I can estimate given this particular state, I don't have to look at all the infinite, gazillions and gazillions of possible states of all of the states of every possible chessboard in the universe. I just need to know, here's my current state, and if I make this move, here's my reward for that, and I can sort of break the problem down into subproblems, and that was Bellman's real insight, right? So some key ideas. This is a model-based learning, so we're using a model here, and hence it's called model-based value estimation. And the next thing we'll talk about is model-free learning. Okay, so this is a model-based learning. It uses a Markov decision process, which simply means that, fancy words for basically means that there's a probabilistic state transition diagram at work here. So I can move into sort of from one discrete state into another discrete state. Dynamic programming means that I'm able to break down a problem into tinier, smaller subproblems. I don't have to try to solve the entire thing at once, and that's what this is the current thing I'm looking at, and these are all the future things that I could be looking at. And this Bellman optimality allows us to recursively optimize the subproblem. So all I have to do is kind of find the best thing in a current state. What do I think is the absolute best move I can make right now? And I can then break the problem down into, well, okay, now I understand that. I could go one step from there. I can take the next step, and in that next state, what's the best move I can make in that next t+1 state? Okay. From a policy, I can determine a value. From a value, I can determine a policy, and I can iterate. So the idea is that I iterate through through the system, through the problem, and I can come to a solution. So hence it's a model-based value estimation. Okay. Now the next thing we'll talk about Q-learning is kind of similar. So it also uses the Bellman equation. And again, we have that same, there's an agent, say Mario Brother, a little digital man who's walking through an environment, or we have a chessboard where I have pieces and a board state. As actions, I can move certain pieces, and as a board state, I have the state of the board is my environment. I observe the state of the board. I get some reward for making a move. Maybe I have points here, or maybe I win the game. And there's certain actions I can take, and there's states. It's called Q learning. Q stands for quality. So I'm trying to optimize this quality function. And that quality function is a function of the state and the action. And so basically, given a particular point in time, there's a certain quality for the move that I'm about to make. And for the move I make, there's some reward, and then I can calculate some future reward. So it's an estimate of the optimal future reward. That's what that gamma max A prime Q S prime A prime is. So the R is the immediate reward for taking some particular action, and this gamma max A Q S A is the estimate of the future reward, and gamma is a discount factor. And why that's there is I don't kind of want the system to continually take the same sort of actions. I might get into kind of a rut. So I discount future actions a little bit so that I give a little bit more weight to my immediate actions. And the fact that I can calculate this estimate of all the optimal future rewards means I really I don't need to look at all the every possible, gazillions of future possible moves. I just sort of estimate in one term the future reward, and then I can just focus on what my immediate reward is, and then break the larger problem down into just looking at my current state. So in an example here, we can calculate a reward for, given this particular board state of a chessboard, and given all the possible moves I could make with my pieces on this board, I can just look at this state, and from there, I can calculate a reward function. I can calculate a reward value. So I can calculate a quality of a move given a particular state and an action. And again, here this is the Markov process comes into play, meaning that each state is not dependent on previous states. Now, Q-learning is really powerful. It's at the heart of AlphaGo. It's at the heart of the Atari DeepMind AI. So in 2014, Google patented a deep learning algorithm, which is a Q-learning algorithm for playing Atari games, right? So this Q-learning concept is really powerful and has been used in playing games to create some really powerful AI machines. So it's a model-free reinforcement learning. The previous thing we talked about was model-based learning. This is model-free. It's gradient free reinforcement learning as opposed to gradient based. So I don't calculate a gradient factor of what my am I moving towards a hill or valley, right? It's off policy versus on policy. So we talked about the policy function pi of, I have a particular policy, I have a particular rules of thumb given a particular action versus a particular state. I'm able to dynamically create this policy. And again, this is an algorithm that's been around for 20, 30 years. Chris Watkins in 1989, in his PhD thesis, was learning from delayed rewards, was sort of the seed of this, and it's grown. Of course, it's grown a lot in those decades, and there's been lots of advancements in how it's used, but the basic seed of that idea has been around for quite some time. Okay, so so in a summary of where we are now, we've talked about artificial intelligence, programs and machines that learn, reason, and make intelligent decisions. We talked about how there's three basic kinds of AI: artificial narrow intelligence, artificial general intelligence, and artificial superintelligence. And we've talked about the four big pillars, the four big ideas in machine learning: machines that learn through experience without explicit programming, unsupervised learning, supervised learning, semi-supervised learning, and reinforcement learning. And we've talked about neural networks, so autoencoders or current neural networks, feed-forward neural networks, and convolutional neural networks. I won't go into deep detail about deep learning, but there's some big ideas as well: convolutional neural networks, transformers, Boltzmann machines, and deep belief networks. But they're just basically more advanced neural networks. So deep learning uses artificial networks they are artificial neural networks with sort of more intermediate layers that can adapt, learn, and make intelligent decisions. And again, I wanted to emphasize that really just scratching the surface, right? There's been lots, there's decades of work behind all of these categories of algorithms, and there's many, many, many more machine learning algorithms that are out there. But many of these are sort of variations on a theme, right? So there's lots of different advancements in neural networks, but the basic concept of I have some input nodes, I do something with those nodes, I have some output nodes, and there's basic things that I can take inputs and feed them back, or outputs and feed them back into the inputs as sort of feedback. I've given you the big ideas, and there's lots of variations on a theme here, basically. So, okay, so I'm gonna next talk about the past, present, and future of AI history and milestones. Okay, so next in this next section, I'm going to talk about the past, present, and future of AI. I'm going to go into some of the key developments and key big milestones and big ideas that have happened over time. I'll talk about AI winters and kind of where we might be going, a little bit of where we might be going in the future. So in 1950, Alan Turing proposed the Turing test as a measure of machine intelligence. So he asked a question, what does it mean to be human, and how can we differentiate a human from a machine? And that basic question is still with us today, right? But in different forms. But he was one of the first to formalize it. In 1956, John McCarthy coined the term artificial intelligence for the Dartmouth College Summer AI Conference. And you look, there's some huge names, right? And Claude Shannon is also a big name in computer and communications science. John McCarthy, Marvin Minsky is a big name uh, the Society of the Mind and AI. Anyway, a lot of big names in that summer conference.
McCarthy McCarthy was a professor at Stanford, and he also wrote some really interesting things about teaching AI, which I thought were really cool.
Yeah, yeah. All of these and Solomonov, all these are big names. Okay, and speaking of Solomonov, in the 1960s, Ray Solomonov used Bayesian methods for inductive inference. We've seen how, this again, we see the Bayes equation again here for prediction for probabilistic inference in machine learning. And, we saw that in one of the machine learning methods. In 1965, Alexei Ivanenko makes the first deep learning multi-layer perceptron trained by gradient descent. So here we see the start of neural networks, basically, right? Uh, and the concept of there's some inputs that we take. Let's maybe one path to artificial intelligence is what if we try to emulate what the brain is with neurons, right? And so that was kind of the idea behind neural networks. Oh, and then we have the first AI winter. So um, basically, there was a lot of excitement in the 50s and 60s about the promise of AI. So, we're in the era of the space race, and there's people are really optimistic about advanced technology. We're coming out of some really amazing advancements in science and technology, and there's the sort of fascination with technology, and to a large degree, we still have that today. But there was so much hype around AI and a lot of investment that didn't come to fruition, partly because computers weren't advanced enough to be able to do what they can do today, right? So between 74 and 1980, there was what was called an AI winter. They overhyped it too much, and there was too much expectation on what it could promise, and when that fell short, the funding dried up, and people sort of lost interest. In the 1980s, backpropagation algorithms spurred a resurgence in machine learning, which is used to iteratively train neural networks to gradually minimize errors. And the concept of backpropagation is basically feedback. So basically, I'm taking the outputs and feeding it back into the inputs, and I'm taking that information and refining my output. But again, there was another AI winter from 1987 to 1994. Again, this too much expectation and too much hype around and too much promise around what we thought AI could do. And when it fell short, people sort of lost interest. However, simultaneously, what's happening is the PC revolution is happening in the 90s. The internet is really taking off. And really computers all the while from the 1950s to you have to consider and even before some authors have argued computer power is doubling every 18 months, 2 years, right? So computing power is really becoming more advanced as by leaps and bounds every cycle of Moore's law here. So in the 1990s, there's a shift from knowledge-driven approach to a data-driven approach. We talked about support vector machines. We talked about recurrent neural networks. Those become popular. And instead of trying to program in all of the possible knowledge in the universe into a machine, which was the method, which we thought was the approach, people started thinking or of that. Maybe if we just try to process and categorize a bunch of data, and I process big data, maybe that's a better approach. And so we shifted to this from knowledge-driven to data-driven approach. And we talked about Q-learning and some of the deep learning methods here for a machine learning to be able to analyze the particular state and to estimate the reward functions and to be able to take a next step, a next move. In 1997, that culminates into Deep Blue's chess machine, which defeats the then world chess champion Garry Kasparov. In 2002, iRobot's Roomba is an autonomous robot that vacuums the floor while navigating and avoiding obstacles, and it heralds the domestic use of AI in robots. And I think if the thing is, in science fiction and movies and TV and stuff, there's this sort of expectation that's set that a domestic robot is going to look like Rosie the robot. It's going to be a humanoid robot that makes salads alongside while you're doing stuff in the kitchen, right? But the first AI robots are really much more like things like the Roomba, Alexa. They're just cylinders, and they're doing very specific, specialized tasks. And so the iRobot's Roomba is really heralded a new generation of robots that we accept, and they're much more kind of like R2D2 than they are C3PO. In 2005, Honda's Asimo robot, which is debuts. It's an artificially intelligent humanoid robot. It can walk, it can go upstairs, it can go downstairs. So it's pretty amazing. But it's not. We don't see Asimo, waiters or restaurateur robots today because the human environment is a really messy, chaotic, and difficult to navigate environment. However, it is a milestone. So in 2005, this humanoid robot that can walk is pretty amazing. I was on the cover of the book that I wrote on robotics. In 2010, deep learning becomes feasible, which leads to machine learning, and we've talked about a lot of the algorithms in machine learning becoming integral to many widely used software services and applications. So deep learning is a form of machine learning, and it really starts to take off. 2011 introduced the Echo, a voice-controlled intelligent personal assistant. So here, it's putting applications of natural language understanding to use, and it's able to decode requests that you give it. The Partnership on Artificial Intelligence in 2016 to benefit people in society formed for the responsible use of AI. So it researches best practices for AI and to educate the public about AI. So, and we'll see here in the next few years, this year and last year and upcoming few years from now, this question of responsible use of AI and ethical AI and trustworthy AI, lots of these topics are cropping up because it's really important now to think about and answer and to try to explore these questions of how could I go wrong, and how do we use it intelligently, basically, how do we use it ethically, and how do we develop it ethically, and how do we develop it such that it's trustworthy. And we saw in 2023, actually, and Becka will talk more in her class about this, I'm sure. There have been more legal cases regarded to AI in this past year than the past 10 years before that.
Yeah. Lots
So
of copyright, lots of misuse of AI,
yes,
lots around hiring. Yeah.
yeah, exactly. So, okay, so in 2018, Hiroshi Shigeru creates Erica, the world's first robotic humanoid news anchor in Japan. In the subsequent years, just even in the past couple months, Ashley, I was messaging Becka that this this chatbot campaign calling AI can call on the campaign behalf, which opens up all sorts of interesting ethical questions and stuff. So, but imagine from there you can go to telemarketer chatbots. So.
Yeah.
Okay,
I mean,
so
this election is going to be all about AI in one way or another.
yeah, oh, yeah, absolutely, yeah. Okay, so in 2020, OpenAI introduces ChatGPT, and unless you've been living under a rock, ChatGPT in 2020 maybe it wasn't so well heard of, but it's just all over the news now, right? So it's an autoregressive language model using deep learning, and however, it hallucinates. So there's a term in AI called AI hallucination, which is basically when an AI produces an answer very confidently, but it's wrong, right? So
Yes.
it basically says, if you ask it, how far the sun is away from the Earth, and it's 98 million miles away, it says it's 50 million miles away, and it's definitely 50 million. I know it's 50 million miles away, right? So it's hallucinating. So it's an example of if it, and I've actually encountered this. I've used ChatGPT, and I asked it, what are the most popular franchises, because I was talking to a friend about that topic, and it hallucinated. It gave the right kind of order of answer, but wrong numerical, answers for how much. However, it found the answers. I don't know how it found the answers, but they were wrong. So when I fact checked it. So GitHub Pilot is a cloud-based AI tool made by GitHub and OpenAI to help Visual Studio Code, Visual Studio, NeoVim, JetBrains users use IDEs, integrated development environments, by auto-completing code. So essentially, it can help you write code. GitHub is super popular. I use it in my work to. It's a repository, for software and stuff, and works well with Python and Java and TypeScript, Ruby and Go. If you're doing anything with AI, you'll hear a lot about, at least right now in 2023, 2024, you'll hear about Python, right? So Python is a low code computer language. I've learned many computer languages in my life. I was a software programmer as part of my career, and it's just so much easier than I've learned many computer programs languages, and Python is just 10 times easier to learn because it abstracts a lot of stuff. It does a lot of, instead of having to write functions line by line, there's this huge libraries and lots of abstraction going on to help you kind of get, it's more sort of word friendly and commonsensical friendly. In 2023, ChatGPT reaches 100 million users. It becomes the largest consumer application ever. It scores 1,400 on the SAT by itself, 163 on the LSAT, 298 on the Uniform Bar exam. It's multimodal, meaning that it can process images as well as words. And I think again, it's ChatGPT has really come into the social consciousness. Everybody's kind of heard of ChatGPT now. It's so much in the news and all over the things that it can do, and I'm sure Becca will explore that a lot throughout her class. Okay, so Google releases in 2023 its conversational generative AI chatbot in response, essentially, to ChatGPT for kind of early. So I think it had been planning to release Google Bard a little bit later than it actually did, but they released it and were really surprised by its responses, and how well it did. It's also multilingual, and there's plugins now to Google searches that you can use it. You can use it, and it's pretty. I've used both, and compared the responses to type the same question in both and compared the responses, and it's kind of interesting to see what it gives. They're very similar, usually fairly similar kind of answers.
Microsoft now has Bing, and you see both Google and Bing at the top now. They have they use Bard or Bing at the top, so you get both search results without any plugins, which I think
Oh
is
yeah, yeah,
interesting.
right. I think that's quite interesting. So I've been giving this intro lecture at Becca's course for a few years, and I went from talking about self-driving cars to sitting and riding in a
Oh,
self-driving car.
really?
So it's really
Awesome.
interesting to see how fast AI is progressing, right? So, and in fact, maybe I'll pause here for a second and just show you a video. Um, so here's a video of my first AI self-driving car ride. So we're in the car here, and it takes off. um, it's swimming in traffic. Now it has two screens, and one of these screens, it shows you these little square boxes you see. It shows you square boxes and white circles of where people and cars are. And and we're sitting in the back seat. There's nobody in the front seat. So it's really impressive. Here it makes a turn, and it just really swims with traffic really well. So at first we were a little bit hesitant to get in,
Yeah.
but it's really amazing. So I think once it makes a couple turns and merges with traffic, it's really impressive.
Did you drive in California?
So this was in Phoenix, Arizona.
Okay.
Waymo is actually the evolution of the Google self-driving car project. And
Okay.
Zoox, which is also in California, as I understand it, is I think I'm not as familiar with Zoox, but Waymo is really impressive. It's in 3 cities right now. It's going to be in Las Vegas. It's currently in Phoenix, and I think it's in Las Vegas. So it's in three cities.
I asked because I know most states now have self-driving car laws,
Hmm.
and many of them require that the person be in the front seat just in
Uh,
case the car screws up.
yeah.
So,
Yeah, so actually, so we did talk to the operator, and it's very easy to talk. You just say, hey, operator, and somebody hops on right away. And so, they ask you, how can we help? Is there anything wrong? And et cetera. So there is kind of contact to the company, and again, you can imagine there's lots and lots of interesting corner cases that could come up
oh yeah.
from driving. So I'm sure Becca will touch on that more. Okay, and 2020, these are some of the big things I think we'll sort of hear or see in 2024. So generative AI algorithms. You've already heard a lot about ChatGPT and Bard, and it's some of all its how it's used and its ramifications, and you hear more of that basically. Democratization of AI, so no code and low code platforms. I mentioned some of these already. So basically, the more abstraction of the coding language, it makes it easier for just a sort of normal person off the street to be able to program stuff, right? So an example of a no code type system is I have some GUI that you can just drag and drop boxes and say, to let's say I'm programming like I have a R2D, I have a little R2D2, I own a little R2D2 robot, right? And you can program it to do stuff by sort of clicking on little boxes to say, hey, move here or patrol here or make a left turn or right turn. And that's an example of no code programming. So basically, I don't need to learn any computer language. I just have a graphical user sort of interface that's very easy to commonsensical. Um, and and uh, um, and we'll see probably more of those kinds of interfaces.
One of their
Augmented,
options for this week is to use Scratch, which is another example of a no-code language.
yes, right. Yeah, like a more graphical way to program stuff. Augmented working, robots partnering with humans and AI-powered virtual assistants. So we see a lot of articles and books. Basically, I think a lot of books I think mention how we'll first see rather than AI trying to do a particular task alone, a lot of times it can be there are a lot of applications that I've read about where people partner with AIs and the AI does the thing that computers are really good at, processing data and classifying huge amounts of data and that kind of thing, and partnering that with things that people are really good at, interacting with other people and doing cognitive and creative sort of things, and those two together form a really powerful partnership. And then I mentioned before AI and sustainable AI, making AI ethical and unbiased. The black box problem of AI is basically, because if we look at like the neural network type machine learning algorithms and stuff I talked about, we don't necessarily easily see kind of what's happening under the hood. But that's the same with your brain, right? Like how do I know how you made that decision? Like
Right.
we have basically your neurons have certain weights that you train over your whole lifetime, and from those, you make decisions. And how do you know you're conscious, and how do you know how do you explain that decision? And you can. There've been lots of interesting psychology experiments about um, if if people have some brain damage, how do people come to certain conclusions, or even if you separate your left eye from right eye and show up image to your left eye and your image a different image to your right eye, how your verbal centers of your brain try to explain those different pictures or connect them is very interesting. So those sort of when you train a neural network, a computerized neural network in machine learning, what do the weights mean? How did I arrive at these decisions? And lots of different the trolley problem in self-driving cars. There's lots of interesting corner cases. I think that'll have already cropped up in 2023, and more will crop up in
And you're
2024.
seeing that area where they're looking at transparency, the new law that the EU passed, the Artificial Intelligence Act, just passed. And some of the laws you're seeing, like New York's AI and hiring ordinance,
Hmm.
a lot of them focus, especially on that transparency, on being able to get behind the black box to understand how decisions are being made using the weighting. So that's definitely an area where law seems to be focusing right
Oh,
now.
absolutely. Yeah. I could see a lot more, and there'll be a lot of, I think, corner cases that we've only just not even scratched the surface of, when the so yeah, we'll see a lot more of that. I feel like coming up. Okay, so now this is a little bit of a futurist slide, so you have to take it with a grain of salt. I'll voice a disclaimer here. So anything in the future is not set in stone, right? So these are just really rough estimates, but they're not necessarily my estimates. So some of these I've garnered from articles and books and surveys and stuff. So, but the rough general, you can sort of see the rough roadmap, right? So we'll have more enhanced narrow AI. We have lots and lots of narrow AI examples now. Everything pretty much we have now is narrow AI, but they'll get better and better and better at doing specific tasks and expanding what they do. ChatGPT and all these other applications that are that some of what I'll talk about in another section here coming up will become just only better. And then we'll come to AI initiated operations and AI art and AI generated software and AI created software, AI solving problems and doing and writing and creating research, starting to be creative. Again, as I mentioned before, it's not going to be this binary, we didn't have general AI and suddenly we do, right? It's going to be a gradual, suddenly there's this article and about this AI that creates art, but is it really art? And it's kind of art and it's kind of not. And then, maybe 10 years later, that's clearly art, and it was generated by an AI. So I think you'll see more and more AI do more and more over time. General AI. So here we have AI with basically all the full cognitive capabilities mimicking a human. Now, um, if you've been paying attention, it's not that the end goal isn't necessarily to be a human, right? The end goal here for AI is to maybe partner with a human or to be useful to society in some way, and that's not necessarily just to have a humanoid robot. You can Alexa and um, Amazon Echo are super useful to society, and they're using AI, narrow AI, and but they're not, it's not a human that's a human-like thing that's sitting next to you. It's just a cylinder, right? So, um, and then super intelligent AI. So at some point, maybe in the far future, and again, this is one that was taken by a survey of like 90 futurists. So they roughly predict, about 100 years from now or so, of AI with cognitive capabilities beyond a human and machine consciousness. So take this with an extreme, the farther out you go, take it more with a bigger grain of salt. So, but we see this sort of general pyramid of machine learning based narrow AI, user-driven big data models for machine learning, things like robots, bots, chatbots, Siri, Alexa, Cortana, to more machine intelligence, stage 2, trained ad hoc models and custom learning to this machine consciousness level. Okay.
You know, Elon
Yeah.
Musk is convinced that we're going to have super intelligent AI in the next 5 years.
Yeah, that's I think that's optimistic, so
I think it's optimistic also.
yeah. So there are many people who are trying to predict stuff, and um nobody has a perfect crystal ball. Again, these aren't numbers that I just pulled out of pulled out of nowhere. There, I've read a lot of papers and books and stuff, and there have been, if you search around on the internet, you'll find lots of surveys from, different organizations and stuff. And these are sort of really rough numbers. And who knows, when I think there will be a there will be a sort of singularity point. Ray Kurzweil coined this term called the singularity point, where basically where when you do reach certain points, like when you do have general AI, things will get really, really fast after that. Things will really accelerate after that. So if we do hit one of these points, a machine that can actually think or a machine that's SQL self-aware, there lots of things could happen after that. Think of an AI that's able to intelligently write whole software systems, right? When you have
Right.
think you can suddenly develop whole nother systems beyond that, and you can do just or think of an AI that can create research, or write research papers. I mean, that'll open up a floodgate of research. Or even now, where AI is kind of creating art and music. There's already in 2023 lots of questions about, hey, is this AI really, is that art? Is that music? And
Yep.
there's lots and lots of legal questions, lots and lots of questions around that. So yeah, and all of these things will sort of cascade and domino onto each other.
And so far, the Copyright Office in the US and the UK has said absolutely not. But
Yeah,
that will change over time, I think.
yeah, yeah. Okay. Okay, so next we're going to talk about AI/ML applications. So how is AI/ML used? What are some practical applications? We've talked a lot of theory. We've talked a lot about the concepts of AI. We've talked a lot about the history of AI winters, and machine learning, all the various different kinds of methods and algorithms in machine learning and neural networks and ANN and RNN and convolutional CNN, convolutional neural networks, deep learning, DL. But let's talk a little bit about more boots to the ground, some applications and how AI might be used. Becca had asked earlier for some of these algorithms, how are they used? And I created a chart for just to answer that question.
Yay.
So in unsupervised learning, here again, the there's no training data that guides the AI. And it's important to note that supervised learning has often a very deep cost, a very heavy cost, partly because somebody has to say, this is the data that, is right or wrong. I have to give the AI sometimes lots and lots of human classified data to work from. And that can be very costly. And that's why there's semi-supervised learning where I can try to lighten that load.
It's also like an ethics question. A lot of people who are labeling data are Mechanical Turk people earning pennies per hour, or people
Mm,
in less developed countries who are doing
yeah,
it for not much money.
yeah,
Um,
right.
but
That's very interesting. I mean, it opens up the doors to exploitation and stuff as well.
yeah,
Sure. So an a priori association that can be used for sales type functions and retail and categorization there. Word associations, and again, we're looking at known prior associations together, search type functions. K-means clustering, again, where I'm trying to divide information. I can look at the monitoring of a system and how well it's doing. I can look at search intent type information. Artificial neural networks is very broad, so it can be used for a whole bunch of different type of applications. But generating new and synthetic data, creating like I can use it to like create a picture of something, for example. So you see like things like Fibonacci or things that are able to take words and generate images from them. Data mining and pattern recognition is also where artificial neural networks shine. So classifying images and those sorts of things. For supervised learning, linear regression, again, I'm trying to plot a trend, right? So sales forecasting is something that you can look at. Like I can take a bunch of independent data, and from there uh, I can forecast a trend for dependent data, or I can assess a risk. If I take these 6 actions, if I'm an insurance company and I'm trying to assess how much risk are you, how much how much should your premium be? I can use linear regression to do that.
one of
Support
the common
vector.
areas you see that is in law is predicting how a judge will decide a particular case.
Yeah, right. Yeah, that's a good example. Yeah, thanks. Um, so support vector machines here, I'm trying to classify a group, a body of data points. So the example that I showed in my slide was image classification. So trying to classify pictures, whether they're cats or dogs. I can also look at financial performance comparisons. I found a way to classify groups of performance data from different companies, and I can try to find a hyperplane between those and classify this is a really quickly accelerating or high performance company, and this is a less performance company. In the decision tree, again, think the 20 questions. You can use those for things like simple predictive analytics. So I'm trying to, given a particular set of data. How do I classify those and predict, where they're going? Or maybe I want to classify how I should price things given different categories of people. And this very simply was also used in the car industry. One of the earlier inventions in the 20s and 30s with cars was the invention of like luxury models and basic models, right? So that idea, is an idea that could be used in pricing, for example. Generative adversarial networks, or GANs, can be used for audio and video manipulation. The example I showed was in fact that, where basically we're looking at basically images or audio or video and to try to produce better audio or video AV type things. Usually one of the networks in the GAN, one of the opposing adversarial networks is something that generates data. So it generates an image or video or whatever to challenge the other network. For self-trained naive Bayes classifiers, those are really good at in NLP, natural language processing. It's good at it's good for classifying language and words. Excuse me. For model-based value estimation, linear tasks and estimating parameters. So, another really good example is like video games. So things that are able to play games or train on games, Q-learning. These two algorithms are good for that kind of thing. Policy creation. So Q-learning is all about making some kind of, given this particular state, what should I do? What's my policy? And then consumption reduction is another example of Q-learning, where basically I have some kind of system and I'm trying to find an optimal way to consume less to make optimal decisions. Okay, and as I started to think, I created, if you've seen my previous overviews on AI, this is a new slide. And as I started thinking about it, like talking about AI or giving an AI overview or talking about applications of AI it's kind of like asking where are computers used. I mean, they're used everywhere. Today,
Right.
computers are used everywhere. So it's a little bit hard to talk about, how will AI be used, because they will be used everywhere eventually, right? You'll see smart and you'll see smart everything over time, right? So from 2023 out to 2033, eventually everything will become smart. But we can start to think about where they're first starting to be used, and we're first starting to see them used more here than in other places, or they're gaining more traction here than other places, or perhaps we're seeing certain interesting cases of certain interesting questions of things, how they're being used. So in the aerospace, I have a friend who's a pilot, and he says AI is used already in just planes to intelligently guide them. The autopilot and stuff is really already very impressive, and that'll only improve. In e-commerce and retail, we saw some of the machine learning algorithms where I'm like, just a really simple example is where I have recommendation engines. So that's a really simple example of where it's used, and AI is used a lot in a lot of places already for sales and forecasting, and a lot of partnership type things where I have smart retail, or things like Amazon Echo and Alexa are also examples of that. In the hospitality industry, so this may not be so as quite as obvious, but you know, the places where there's little computerization, where there's has the most to gain, right? So I drive a Toyota Prius, and and I've driven a hybrid car since June 2 of 2000, and the Taylor designed hybrid cars are very efficient. I'm getting 50 plus miles per gallon, right? And if you look at a if you look at a sedan that's been converted to be a hybrid, its gain isn't quite so big. But the biggest gains to be made are converting 18-wheelers or converting SUVs into hybrids, right? So the same in the hospitality industry, the wider the gap, the more there is potentially to gain. So it has a potentially, a lot potentially to gain in AI. But that said, it's also one of the more high touch industries. So um, there are industries that even 100 years from now, you won't have AI. Like a firefighter is, not likely to have an AI firefighter, right? Or a plumber.
We
You're always
do
gonna.
have, but their firefighting is now using computer dogs.
Yeah, yeah. I mean, they'll partner, but like you always need
Right,
people to carry people.
right.
You'll need a plumber who those sort of high touch things. You're not
Yes.
going to have a robotic AI president for a long time, right? You're
No.
not going to have a you're not going to have a HR, PR, public relations person, right? Any sort of high touch where you need to interact with other people, and certainly the hospitality industry is one of those. But you'll see AI infused in lots of things in the hospitality industry and real estate, where you can take virtual tours and robotic assistants showing you a place before you go there. In the agriculture, um, the automation of agriculture with smart fields and the use of what's called IoT, the Internet of Things, we'll see advancements here. Industry 4.0, I have a whole slide on this. We'll come to that. In the defense industry, of course, it's used. It's the even though I'm not a big proponent of things that machines that kill things. Um, it is a lot of money gets poured into the defense industry, and of course, it's paving the way on a lot of things.
We're
Banking and
already seeing
finance.
it being used in war in many ways. So, yeah.
Yeah, I mean, I think it will be. It scarily could be used in a lot of military applications, and I'm sure that it's already. There are lots of AI-based type projects in the defense
Yeah.
industry already, which is quite scary for me at least.
Terrifying. I mean,
Yeah.
you're seeing AI drones being used a lot for like surveillance and spy
Yes.
purposes. Is
Right.
one of the more one
Right.
of the less scary options, which is saying
Yes.
something.
Yes.
Yeah.
I recently read a book called "When the Heavens Went on Sale." I recommend anybody to read that. It's a very interesting book about the sort of recent history of these um, rocket small rocket companies and things like the Falcon, the Elon Musk's uh, the rocketry programs that have really spawned a lot of rocket companies who are basically going to launch a bunch of smart satellites in low Earth orbit, right? So and can do whatever. So that I think we'll see a lot of interesting applications. Hopefully for the good, but possibly some for the bad come out of that. Now, banking and finance, AI really shines when you have a ton of data to go through and a ton of data to process in some way. And of course, banking and finance, for purposes of making your transactions smoother, to find fraud and things like that, are already used there. So that has probably and if you read a lot of books and read a lot of articles, banking and finance is probably one of the industries that has made the most progress on AI because of its very heavy numerical and math-based sort of dependency. Insurance. So now you might not think insurance would be a place where you adopt AI, um, but it's also quite mathematically intensive, right? So I want to figure out, how much of a risk you are. I'm constantly looking and finding out statistics of the population, for all sorts of things. How likely is it when you're in an airplane that you'll crash, or and that you buy this car you'll crash, or that you're in this particular age bracket that you'll crash, or that sort of thing. And to calculate the life insurance and health insurance and automobile insurance, they all use. That's a lot of number crunching, and we'll see a lot of applications there.
What
So
I
we've
like
talked.
what I like about the insurance one is it let them do customized rates. So they've had algorithms in insurance since my grandfather was selling insurance in the 50s.
Oh yeah, yeah,
Um,
yeah, yeah,
but
yeah.
it used to be that it was like, if you're a male and you're under 25 and you're not married, you're the highest risk. And now they can look at a lot more factors to better tailor rates for people, which
Oh,
I think
absolutely.
is a good
Yeah.
thing.
Yeah. Basically, a lot of those things that were hand computed or maybe computer compute, like a calculator computed, are now becoming AI, computed, and a lot of they're just smarter and better estimations of things, of sort of concepts that were around for a long time. We've talked about smart transportation, and Becca will talk a lot about legal, so I won't talk too much about that. In communications, this is my work area, so I work in telecommunications. So we'll see smart and media and AV applications and social networks. We'll see a lot of these are also very computer and number and data driven type of industries. So, there are a lot of smart and tailored type things and experiences we'll see over the next decades as well. In politics and government, and again, this is one of those sort of high touch areas. But we'll see applications in politics and government coming up in the next things here. So the three broad pillars I have, and these are just my sort of categorizations, but things related to industry, things related to community, and things related to personal. So on the personal front, we'll see AI in entertainment, not just in sort of AI created stuff, but also in how it's used in things like your streaming services and things like that, right? So we'll see AI transform or help productivity gains and productivity applications in the workplace. Intelligent personal assistants, which we already have, things like health trackers and Siri and things like that. In sports, so things will, if you've ever looked at smartwatches, they'll become even smarter. But things like smart metrics, looking at your sleep patterns and your diet and things like that, and your exercise, they'll become better and smarter. I have a whole slide on smart homes, so I'll get to that in a second. Healthcare applications. So this is also one of those industries that took a long time compared to many other industries to digitize. So for a long time, uh, computers were not as infused in the healthcare industry. You had to fill things out in triplicate and a lot of errors, made by hand in this industry. And doctors and nurses are notoriously anti-computer or slow to adopt computing capabilities. But that's changed in the past, I'd say, 10 years. So that you can imagine, because there's so much more potential possible growth, because it was so not computerized, that lots of companies have made inroads and improved that situation.
What
Of
I
course,
love
game.
about like the human partnerships we're talking about, you're seeing a lot of partnerships where for example, the AI helps find tumors, and then
Mm,
a radiologist verifies that, and
yeah.
it's pretty
Yeah,
cool.
absolutely. Yeah. There's lots and lots of examples. Just the pure amount of data management of your vaccine record, your health record, and your surgery record, all those things, and also lots of prescription management and medicine management, things that misprescribing medications as a huge was thousands of people died
Yep.
there, and also finding patterns. So the whole OxyContin problem that we've had in the U.S., where people are addicted to opioids. You can find statistics now through AI of lots of people dying and trends and things like that. That's just
Yeah.
tailor-made for the use of AI. Yeah. So in gaming, of course, gaming is all lots of data there and lots of popular things there. So AI has already seen a lot of inroads there. And of course, education and learning here, we'll see AI improve our ability to process and adjust and learn. Okay, I won't go into these next few slides in great detail, but basically you'll see a lot of applications in smart homes. Um, so I will note that the home is a difficult environment for AI and robotics, just because you have kids and things are messy and there's lots of possibility for problems and errors, and it's a very difficult situation for any robot to navigate. But you will see lots of narrow, specific applications to control lights, to control your environment, to security cameras and smart locks and smart doors. And a ring and smart lighting and stuff. So we'll see a lot of those kind of narrow applications, and those will grow over time. The smart cities, similarly, you'll see lots of more intelligent emergency services, power management, public safety, smart meters and smart parking, navigating a city, augmented reality, the Internet of Things, where things talk to each other more intelligently, the connect car services, sanitation, water management. And we're heading into Industry 4.0 here. So basically, the first Industry 1.0 was about mechanization and steam power, the weaving loom. Industry 2.0 was about mass production, the assembly line, and electrical energy. Industry 3.0, automation and computers and electronics. And Industry 4.0 is really characterized by artificial intelligence and robotics, smart, basically the smart factory. So we'll see lots of applications of smart things, factory lines that can reconfigure themselves, robotic arms that are more intelligent. There are already robotic arms in Industry 3.0, but robotic arms that can do smarter things, that can reprogram themselves and such like that. Okay, and in this last section, I'll talk about some of the AI ML players, and I'll mention that this is growing by leaps and bounds. I mean, this is the number of AI players is huge. So, uh, there's so many AI ML players now. I can only just sort of touch the tip of the iceberg. And it's kind of like saying, if it's again talking about AI is starting to talk about like, how are computers used? Well, they're used all over the place, and what companies use computers? Well, just about every company uses computers, right? So there are a lot of AI players, and they're growing quickly. All the big players, Microsoft, IBM, Amazon, Salesforce, and Apple, Facebook, Google, they all have, you can imagine, AI departments, and they're pushing the state of the art in AI and doing interesting things. Microsoft's Cortana, IBM's Deep Blue and Watson, Alexa's Echo and Amazon Echo and Alexa Voice, Salesforce Tempo, Apple's Siri, and Facebook's DeepFace and Fair, and Google's doing all sorts of projects, TensorFlow, Google Now, and so forth. I listened to an interesting talk on the AI's Google's AI roadmap for where they're headed and where their sort of vision for AI. I encourage you to just search on the internet. You'll find videos on Google and AI. And I thought it was really good. So they have a pretty good view of where they're headed, where they are, where they want to go. And they kind of classify it into three major areas. So AI for social good, to try to do good with AI for disaster recovery and solving world problems and healthcare. AI for creativity, so using Party and Finaki to do creative things like making music or making videos or creating images. And of course, Google Translate is fantastic, right? Most people here, watching or listening to this video, probably have used Google Translate, whether at the web-based or the application, and that's just expanding and getting better. So Microsoft is also doing a lot of things. The Innovation They have 5 sort of categories: Innovation Sandbox, the business accelerators, scenarios, and AI for society, autonomous systems, and security responsibility. So they have a bunch of different applications as well, pushing the state of the art in AI. Amazon artificial intelligence projects. Now, these may not be quite so famous, but they're also doing a lot of things as well in computer vision. So one thing I will say, I'll stop here for a second. So one of the things we've learned so far to date about AI and smart things is that what we once thought was difficult turns out to be not as difficult as we thought. And once what we thought was easy turns out to be much harder than we initially thought from the 50s and onward. What I mean by that is computer vision. We take vision as human beings so much for granted, and we do it so automatically. But for a computer, it's just a bunch of bits. Like an image is just a bunch of numbers, right? And from all those bunches of numbers, I have to tease out that well, this group of numbers is a cat, and this group of numbers is, a bird. And it gets much more complex when you throw in shadows and you only have partially hidden. Like if we put a glop of peanut butter on a cat, we still know it's a cat. Or if we put a hat on a cat, we still know it's a cat. But for a computer, it has to learn all that stuff. Computer vision is a much harder problem than we initially thought from the 50s and 60s and 70s. And things we initially thought, this is a measure, like being able to play chess. Of course, that's a very high cognitive sort of function. If a computer can play chess, it can do everything. It's AI. But it turns out that sort of narrow function, that narrow, chess follows a very strict set of rules. There's a finite 8x8 board. There's only so many pieces, and and there's only so many things that it has to consider. And even though there's lots of board positions, it's a very well understood kind of rules-based problem, and AI really shines in that kind of context. So when you think about how we're applying AI really shines when you have a ton of data to process, or you want to group data, and you want to and those sorts of things is where it really can shine. So Amazon has like data extraction, language AI, customer experience, business metrics, code development, DevOps, industrial AI, and healthcare applications. So lots of interesting applications in all some of those major areas that I talked about earlier. So now there are so many applications in AI, and they're growing very quickly. These are just a few, tiny, a few, but kind of very interesting applications I've found, I ran across. So one is called MySkin. It's a dermatology as a service. It's AI-driven skin monitoring. It's application that can find like lesions and carcinoma detection. So during COVID, it was hard for people to visit doctors, and this application could basically use the camera on your smartphone to basically take pictures of your skin, and through AI, it could basically sort of do some of the things that a dermatologist would do to find changes in your skin patterns, and identify weird patterns. And it would send, and you'd work with the dermatologist who could, as an expert at looking at that, at your skin patterns and stuff as well, to help identify problems. Kira is one of, there are many. Kira is one of the applications that have come up in the legal area. Legal services delivery, automated discovery, due diligence, and content extraction. So again, the things that computers are great at is processing and going through zillions of pieces of information, right? So in that e-discovery, when you have to process 1,000 to 10,000 documents or whatever, it can point a lawyer to, you maybe want to look at this paragraph, or you may want to look at this document. So again, partnering with people, lawyers, and trying to make their job easier. Grab Health is a healthcare application. It's mobile medical telemedicine. It's a whole ecosystem. And I think we'll see more of this. This is in Southeast Asia. It's not so prevalent in the USA. But that kind of application where it's partnering with the doctor, trying to assist the doctor remotely, and trying to ease a already heavily loaded and strained medical healthcare system through smart apps. So to be able to track your symptoms and diagnoses and health over time. And as we have more and more monitors, like Fitbit type monitors, that can track your health over time, they'll get better and better at being able to provide guidance to keep you healthy. So Lilt is interesting. It's a contextual AI engine for translation. It's a human-in-the-loop collaborative translation. So it's said to be much more efficient than just a human translator. And if you've used Google Translate, it's not perfect, especially when it comes to things that are much more technical. So maybe just everyday sort of conversational sentences is not so bad. But if you add in very technical things, or some things that you're trying to translate a legal document or a healthcare document or a technical specification, those sort of automated translation things aren't as great. But purportedly, Lilt can really boost a person who has that job and make their job a lot easier.
They're also really bad. Machine translation is also really bad at like jokes and metaphors and like aphorisms.
Yes, yeah, that's a great example. Thank you. Yeah, definitely. And Miso Robotics created this machine called Flippy, which is good at fast food preparation, AI vision assisted robotic food preparation machine. And I've watched a little video of it. It's basically a burger flipper, but it can make all sorts of different foods actually. And of course, the restaurant industry is a high touch industry, right? So you aren't gonna anytime soon see the replacement of people in the restaurant industry with robots, but they can help. And examples of all of these things I point out here are interesting because they're examples of partnering with people to machines. And by the way, all these are from a book called Working with AI: Real Stories of Human Machine Collaboration by Tom Davenport and Steve Miller. And they talk about other applications as well, but I thought these were very interesting. And I've found many others as well since then. But I think these are quite interesting. So in the appendix, I have a chart of many more companies. So with that, we're going to summarize with the big takeaway slides. I think that if I had to pick one slide um, with that sort of summarizes everything that I'd like you to walk away with, or the first thing, the way the human mind works, you'll forget a lot of things. I've put a ton of information into your short-term memory, and for you to, I think it'll benefit you to refresh that by going to at least the summary slide. So. And anything you learn as a student, you want to refresh your memory within 48 hours of learning something. Just go over the information you get, or write a short summary to yourself. But here's a one slider of the whole talk so far. So I talked about a lot of concepts, but there are four big key ideas that you'll hear and have probably already heard of in your everyday life. So artificial intelligence are programs and machines that can learn, that can reason, and make intelligent decisions. Machine learning are machines that learn through experience without explicit programming. Neural networks are connected elements that process data, adapt, and learn. And deep learning is a form of neural networks, which are artificial neural networks with a lot more hidden layers that can adapt, learn, and make intelligent decisions. We talked about three basic kinds of AI: artificial narrow intelligence, artificial general intelligence, and artificial superintelligence. And we talked about a lot of different machine learning algorithms and methods, but they all fall into four basic categories: unsupervised learning, supervised learning, semi-supervised learning, and reinforcement learning. We talked about different kinds of neural networks, autoencoders, recurrent neural networks, feed-forward neural networks, convolutional neural networks, and GANs. And deep learning, there's lots of algorithms in here for deep learning as well: convolutional neural networks, transformers, Boltzmann machines, and deep belief networks. So I hope you found this useful, and again, come back to this summary page. And this is really just the tip of the iceberg to help you explore further. You can find books, and hopefully it'll help you understand, at least conversationally, be able to understand some of the articles and books and videos that you come across on these topics. Okay, so